So the last thing we did last time is we used some of the tricks we developed to graph a polynomial once it's factored. And the rough logic was, if we want to think about this example, well, the first thing that's easy to read off from this is the x-intercepts, right? As soon as you have something factored, it's relatively easy to detect the x-intercepts. Because of this, I know that x equals 0 should be an x-intercept. I know that x equals -1 will be an x-intercept, and x equals 2. Fair enough. The second thing I see is the thing that caused the x-intercept at 0 was just a degree 1 factor. So I know for a fact that close to x equals 0, it'll be a straight line. In order to figure out whether it's like an upward traveling line or downward traveling line, well, plug in zeros for all of the other x's. -8x, so close to x equals 0 should be a downward pointing line. Cool. And now just do the same at each of the intercepts. At x equals -1, I see a square term. So it'll be a parabola. To figure out whether it's an upward pointing parabola or a downward pointing parabola, replace all of the other x's with 0. No, not 0, -1. And you wind up with, I guess, 27 times x minus 1 squared. In particular, it's a positive number times x minus 1 squared. When I'm drawing these cartoon pictures, do you think I care if that was 27 or 5? So if you could even just get down to the point of saying it's a positive number times x minus 1 squared, that's good enough. And you can, right? It'll be, well, let's see, even if you made it this far, negative times a negative cubed, that's like 4 negative signs, that's positive. Get something positive there. Close to x equals 2, you'll see a cubic term. Plug in 2's for all the remaining x's, you get a positive. Hopefully between. And finally, asymptotically, that'll just look like x to the 6th. So it'll look like an upward opening copy of x to the 6th when x is really big. But a reasonable summary of what we did at the end of last time. So, let's do one more. Here's another factored polynomial. Y equals x squared x minus 2 to the 4th times x plus 1 to the power 1. Let's go through the same steps for graphing. I think the two ways I might want to proceed is I can be quiet and let you all discuss with each other and then we come together. Or I can keep talking. Should I just keep talking? All right, let's do. So, step 1, locate the x-intercepts. So, for this particular function, where are its x-intercepts? You set that equal to 0, what is x? 2, -1, and 0. Does that agree? Cool. I don't have the example in front of me, so I believe you. Do I believe you when I look at it? This one produces an x equals 2, x equals -1, x equals 0. Yeah. I see I was not exceedingly creative when I came up with these two examples. That's the same as the previous problem, isn't it? So let's play the same game next. For each of these roots, I will try to record which factor gives me the root there. That'll tell me whether it's like a parabola or like an x to the 5th or a straight line near that point. and then to figure out whether it's positive slope or negative slope, or upward opening, downward opening. I'll replace all the other x's with the location of the intercept. So let's go ahead and do it. So I think I'll follow the strategy where I do one, and then I leave the other rest to you. So I think I'll address near x equals 0. Then I'll let you do x equals -1, and you do x equals 2. So let's do it. So near x equals 0, I need to record the factor that resulted in the x-intercept at 0, and that's the x squared term. So y is approximately x squared times. So I already know the graph will look like a parabola near x equals 0. I just need to know whether it's upward opening or downward opening. So I'll plug in zeros for all the other x's. 0 minus 2 to the 4th times 0 plus 1. You know what, I think I'm feeling particularly lazy. I don't want to do the arithmetic to decide exactly what that coefficient is. Is this a positive number times x squared or a negative number times x squared? You're calling for positive? Do we agree? All right. And right, why was it positive? Well, could you do it by actually just computing what the positive number was? I see 4 negatives in a row, so that's a positive times another positive. Maybe you know that 2 to the 4th is 16? But I don't think I actually care. It's a positive number times x squared. So that means close to x equals 0, should I see an upward opening parabola or downward? If it were negative, I'd flip it, but it's not negative, so it should just stay a parabola. So close to x equals 0, I'll see a happy little parabola. All right. Same game near x equals -1. And x equals 2. So I woke you up and told you all to think about the remainder. So for each of these, I think the type of answer that I want is something that's either positive or negative times x to a power. So near x equals, oh, not x to a power. This would be a shift. X plus or minus a little bit to a power. So, near x equals -1, what is this function close to? Let's see, first things first, which of the factors resulted in the x-intercept at 1? Oh, and -1, yeah, sorry. Which of the factors above resulted in this x-intercept?
Oh, the x plus 1.
The x plus 1 factor. So I need to remember the x plus 1. To the power 1. So that means that near x equals -1, I'll see a straight line. Now I just need to decide positive slope or negative slope. So plug in -1 for all of the remaining x's. Tell me what you get. Are you on call for positive? People agree? Excellent. And maybe you could compute what that positive number is, but I don't think I care. So that means close to x equals -1, I should see a line with positive slope. So it'll crash right through the x-axis there. And then I'll just interpolate it. Same game, near x equals 2, I should see plus or minus x minus 2 to some power. And the plus or minus, I don't literally mean plus or minus, I mean a positive number or a negative number. So, tell me, which of the factors of this function caused the intercept at x equals 2? Yeah, just say that or x minus 2 to the 4. So that means I should see an x minus 2 to the power 4. Good. The coefficient next to it, will it wind up being positive or negative? Positive. So how do you get that? You just plug in x equals 2 for all the remaining x's. 2 squared. Cool. That's positive because it's squared. X minus 2 to the 4th. There's the piece that you just have to remember. 2 plus 1. Oh, cool. That's positive 2. So that means close to x equals 2, I should see a broad opening copy of y equals x to the 4th. So maybe I'll try to draw that. It's like a squared off shaped parabola. Interpolate smoothly between, already done. For big x values, so what's the degree of this polynomial? Sorry, the whole big polynomial. Well, this will kick out an x squared. That'll kick out an x to the 4th. That'll kick out an x. So in total, the degree will be 7, I guess. And I put a blank there because I haven't said what the leading coefficient is. But I think it's easy to compute the leading coefficient of this one. So imagine you did FOIL this out all the way. What's the coefficient you get in front of that x to the 7th? I hear a 1? Yeah, cool, because all of the x's have a 1 in front of them. If there had been like a 3 next to that x, I guess it would wind up being 3. Nice. And we know what y equals x to the 7th looks like. And it looks something like that. How'd that procedure seem? Reasonable? Nice. And I think the homework assigned for last time was exactly one of these examples. So try to walk your way through it. Maybe in order to check, and also because I think it will illustrate something that can happen with a computer-generated graph. Let's also graph it. That's also electronically graphed. We've already graphed it, right? We already have this graph. Let's graph y equals x squared times x plus 1 squared times x minus, Chris. Graphing the wrong example. X minus 2 to the 4th, x plus 1. Does that more or less agree with what we graphed? Yeah, maybe you'll notice a few things. When I wound up drawing those two peaks were like the same height, but I didn't do anything to check how high those peaks should be. It turns out they should have been higher. But that's okay. I wasn't suggesting that this graph would contain that information. If you wanted to get that information, really the ideal trick is, again, some things from calculus to locate where those peaks will wind up being. Groovy. That seem all right? Nice. And maybe I'll also point this out. If we use the wrong viewing window, maybe we use that viewing window, we don't see all the structure on it. If you just result in a computer-generated graph and just copy it down, you won't reveal all the structure that I want to see. So think about your viewing windows when you use a computer to generate a graph. Groovy. So the takeaway from here is once you have a polynomial factored, you can do things with it. You can set it equal to 0, for example, and solve. That's nice. But how do you actually find those factors? How do you actually factor a high-degree polynomial? It's hard. So what I'm going to do starting today and into next time, Wednesday, is I'm going to try to develop tricks to apply to the question of what are the roots of this high-degree polynomial. And before I do that, I want to say a little bit of history, which will culminate in the answer to this question being, it's like theoretically different. So, quadratic formula, the formula you already know, dates back to antiquity. It wouldn't have been written down the way we write it down now by like the Egyptians, because their number system wasn't the same as ours. And that, fine, there's this quadratic formula. It was used in like the pyramid building. In the 1540s, there appeared a cubic formula by a mathematician named Cardano. And so what does that mean? That just means it is a formula that solves an arbitrary degree 3 polynomial. So there's just a formula that solves x cubed plus bx squared plus cx plus d equals 0. How many people have ever seen that formula before? Oh, you have? Oh, cool. In general, I expect that answer to be like, no, because it's too complicated to write down. I'm not going to write it down now. And you can find it. It's like a result in history of mathematics. It's got a Wikipedia page. But it takes probably a good solid couple lines to write down the formula and explain all the terms. A little bit after that, a mathematician by the name of Ferrari produced a quartic formula, which is exactly what you think. Instead of solving a degree 3 polynomial equation, it solves like a degree 4 polynomial equation. It probably takes about a page and a half to write down the formula and all its details. So it's too complicated for a human being to reasonably use. Maybe I'll ask this. How many people have like interest or aptitude in like some coding? Okay. If you said yes, then I'd say, well, you can look up this formula and implement it. And then, voila, you can now ask your computer to solve this degree 4 polynomial equation, and it's doing only things that you told it to do. It's not a black box anymore. So there's a formula that solves any degree 2 polynomial, the quadratic formula. There's a formula that solves any degree 3 polynomial. There's a formula that solves any degree 4 polynomial. What about degree 5 polynomials? It seems like maybe you can just keep playing this game, right? Something weird happens at degree 5. In that in the 1820s, a French mathematician by the name of Galois proved that there is absolutely no purely algebraic formula that solves a degree 5 or higher polynomial equation. An arbitrary degree 5 polynomial equation. In fact, this specific equation, x to the 5th minus x minus 1, has no algebraic solutions. Meaning that no matter how you try, you will never write down a formula for x that solves this equation. That uses only addition, subtraction, multiplication, division, raising to integer powers, square roots, cube roots, things like that. So that's like deeply upsetting, because that's not even that complicated looking at polynomial equation. So if someone hands you a high degree polynomial equation, chances are decent that there is no algebraic solution. That being said, is there still like, if I asked you what are the solutions to this equation, they just said, well, I want them accurate to the thousandths place. What's something you could do? I'll ask you to keep the phone put away. Thank you. Could we graph this? And the graph isn't going to be able to tell us the roots on the nose. But we can, using the normal like zooming in trick, find as many digits of the roots as we want. Let's do that. So let's try to find the roots of, exactly this polynomial equation. X to the 5th minus x minus 1. So I guess here's the first question. How many solutions does this equation seem to have? Just the one? And if I wanted to know about what it is, well, it already looks like it's a little bit bigger than 1. Oh, Chris. It looks like that solution is 1.65-ish. Cool. So you can still find the roots visually, numerically, by just checking a bunch of points. That's exactly what a calculator does when it graphs the thing. And that can let you get as many digits of the roots of a polynomial as you want. So you still have that option open to you. But it'll never tell you exactly where the roots are. This is telling me this has solution x about 1.1. Well, it looks like it rounds up. 1.17. Good enough. I don't know exactly what the root is, but I know it's somewhere around 1.17 by looking at this graph. All right, so with that out of the way, I'm telling you for a fact that in general, there is no algebraic approach that solves polynomial equations. That being said, let's try to find algebraic approaches that try to solve polynomial equations. They're doomed to failure often, but when they work, they give you lots of good information. Seem sensible? So here's the first. If you can find one root to a polynomial equation, then you can reduce this polynomial equation to multiple smaller polynomial equations by factoring. So let's go through and do that. Here's an example. Let's suppose I give you this fact, 2x cubed minus x squared minus 7x plus 6 equals 0. Let's suppose I tell you for a fact that x equals 1 is a solution to that polynomial. I guess you don't even have to just believe me. Plug x equals 1 into that formula. Do you get 0 at the end? Cool. Okay, so I haven't just lied, which, I mean, it's always possible when I write these things. I've been more careful with the examples in this section because it's important. The examples are carefully chosen to walk. So what does that mean? If x equals 1 is a solution, that means x minus 1 must divide evenly into the polynomial I want to study. Which means 2x cubed minus x squared minus 7x plus 6 can be realized it's equal to x minus 1 times something. And let's just think about what that something could be. What's the degree of the polynomial on the left of that equal sign? Three, right? The degree is the biggest power you see? Not the biggest coefficient. X minus 1, what's the degree of that polynomial? The degree is 1. So this is a degree 3 polynomial. The biggest x I see there is x cubed. This is degree 1. So what's the biggest power on x I could possibly see in the something? 2, because 2 plus 1 is 3. So this thing has to be degree 2, since 2 plus 1 is 3. If I could find that something, then I'd be able to use the quadratic formula and just find all the solutions that way. So if I can do this bit of factoring, which I know theoretically I can do, can be done. Let's use the passive voice. We will do it. then we'll be able to simplify the problem by degree 1. We'll be able to then use the quadratic formula, and we have our solutions. So let's try to do it. So what I'm about to do is something which presumably everyone's seen at least a little bit in the past, and that's polynomial long division. And people would say they've seen polynomial division at some point. How many people would say they would like to see like a half-hour long just discussion of polynomial division to recall how to do it? Okay, well, if you do want that, there is such a video posted to the course webpage now. Well, let's go through and try to build polynomial division slowly. So I'm going to approach the same problem, finding this thing, how this thing factors, 3 different ways. And I'm going to go in order from one where every step will make sense. There's no like hidden notation. All the way to the end where if you don't already know what the notation means, it looks like gibberish. So let's do that. So I want to realize 2 times x cubed times x minus x squared minus 7x plus 6. And I'd like to realize it as x minus 1 times something. So let's focus on this biggest term, this 2x cubed. I'd like to turn it into something that x minus 1 divides evenly into. And right now it doesn't. But what if I saw 2x cubed minus 2x squared? Does x minus 1 divide evenly into that? It does, right? Right, it's 2x squared times x minus 1. So, here's the game I'll play. I will subtract an extra 2x squared, but to do that I have to add an extra 2x squared. No, I want to use colors carefully. Plus 2x squared. That's not, the color doesn't show up well enough. There we go. Minus x squared minus 7x plus 6. Don't want to set it equal to 0 right now. So, I guess 2 questions. First, do you agree that what I just wrote down is equal to the thing on the preceding line? Yeah, I just added and subtracted a single thing. Hopefully that single thing is helpful. If it's not, then it's a bad move, but it's not wrong. So, let's carry on. The whole reason to do this was so that I could factor out an x minus 1. So the pink bit factors as 2x squared times x minus 1. All right, and now let's simplify the rest. 2x squared minus x squared is equal to, when you combine those 2 terms, what do you get? Just a plus x squared? Plus x squared, and that's where I will focus my attention next. Minus 7x plus 6. Oh cool, let's play the exact same game again. I see an x squared. So I will focus now on this piece. So the pink bit will just come along for the ride. 2x squared times x minus 1 plus x squared. And again, x minus 1 doesn't go evenly into x squared. But it would if I saw x squared minus x, wouldn't it? So let's do that. Let's put an extra minus x there. To undo that, we'll put an extra plus x there. Then we'll perform this exact same step again. X squared minus x plus x. So there's what I have inserted into this thing. Minus 7x plus 6. Color coding is failing me. All right, so the pink bit I'll leave alone. I want to get x minus 1 as a factor. I already have x minus 1 as a factor, so. X squared minus x, does that now have x minus 1 as a factor? Yeah. How does this bit factor now? Everything has an x next to it at least, so I can factor out an x. And then what am I left with? X minus 1. Oh, hey, that's exactly what I want. I want everything to be a multiple of x minus 1. And now carry on. Plus x minus 7x leaves me with minus 6x plus 6. And now let's just look at this last term. Does x minus 1 factor into that? Yeah, it is x minus 1 multiplied by minus 6. So this bit is negative 6 times x minus 1. And I guess I have to include everything. X times x minus 1 minus 6 times x plus 1 plus x minus 1 to x squared. All right. And let's put equal signs between all of these because they are all supposed to be equal. Does everything there now have an x minus 1 next to it? So can I factor out that x minus 1? Awesome. This will be 2x squared plus x minus 6 multiplied by x minus 1. How did that feel? Hopefully it felt a little bit algorithmic. Right, just look at the biggest terms one at a time. Think about what you'd like to see next to them in order for the x minus 1 or whatever you want to divide in to divide in. Add those things and subtract those things. Factor x minus 1 over the terms you can factor it out of, and then simplify what's left. Oh look, what's left is reduced in degree by 1. So play the same game again. I see an x squared. If it's on x squared minus x, that would make me happy. But I don't, so, but I could. It would be x squared minus x, and I can add the x. Now we can divide x minus 1 out. And I just keep on marching down. So on the one hand, like, that was totally explicit. Each line is just literally equal to the line before it. This is also more work than the other two options. It has the advantage in that it's easy to reinvent on the spot. It has the disadvantage that it's like more steps. So with that out of the way, let's also write this in terms of the long division algorithm. So let's do some long division. So to perform long division using this notation, let's start with this. Let's just look at the biggest terms inside of the division symbol and inside. And let's just think, what do you need to multiply the thing on the outside by to get the thing on the inside? What do you need to multiply x by to get 2x cubed? Yeah, say it louder than that. 2x squared. And then the mindset is that, like, that's going to be, like, the first guess for what the result of division will be. But it's, like, obviously not just the result of division. So in order to see what we're off by, I'll multiply this by that and subtract it. And I'm going to use the fact that I have an erasable pen in the next step, so if you don't believe in erasing, then hold off on writing for a second. So then you'll subtract this times that. So subtract 2x cubed minus 2x squared. So I take the thing that you just did and subtract it from the result. That sounds a lot like just long division so far, right? That's exactly what you do when you want to say, like, divide 11 into 736. So this is why I said I was going to take advantage of erasing. I'm going to distribute that minus sign. And I'm going to do it by just erasing this parentheses and turning that minus into a plus. Fair enough. And I guess I need to erase this parentheses too. And now do the subtraction. 2x cubed minus 2x cubed is 0. That's good. That means we're reducing the degree of our problem. Minus x squared plus 2x squared is plus x squared. And depending on whether or not you want, you can carry these terms down. Maybe it's helpful to do it, maybe not. Let's get the next term. What do I need to multiply x by to get x squared? X. So next term will be plus x. Now I multiply x by x minus 1 and subtract the result. So x times x is x squared, but I need to subtract it. X times negative 1 is negative 1, but I need to subtract it, so it'll become plus x. X squared minus x squared is 0, and negative 7x plus x is minus 6x. Carry this term down, plus 6. So far, so good? All right. Again, what do I need to multiply x by to get negative 6 multiplied by x? Negative 6. This is nice in that it's like the type of question that contains its own answer. Minus 6. And on the one hand, I already knew that division should go in evenly. So I know that there will be no remainder term, but let's check that there's no remainder term by doing it. Minus 6 times x is minus 6, but I need to subtract it. Minus 6 times minus 1 is positive 6, but then I need to subtract that. So this says the same thing. It says 2x cubed minus x squared minus 7x plus 6 is equal to x minus 1 times the polynomial we just found, 2x squared plus x minus 6. That seem all right so far? So again, hopefully that felt like less walk than the ad hoc division that we did in the first column. But unless you already know what a bunch of the notation means, it's not so clear what we just did. But you've all also seen like the long division algorithm at some point, so hopefully that felt reasonably familiar. So there's another further compression of all of this notation called synthetic division. So here's what I'll do. Whenever you want to subtract something that looks like x minus a constant, so since it's x minus 1, I'll stick a 1 there, with the idea being that like that 1 is all the information I need to remember from the thing I'm dividing in. And now I'll just list the coefficients. 2x cubed minus x squared minus 7x plus 6. And the synthetic division algorithm you can now perform totally mindlessly. First I'll take this 2 and write it up here. 2 times 1 is 2. I'll subtract that. Nope. 2 times 1 is 2, which I put right there. Add those, you get 1. I'll take that 1 and copy it down right there. 1 times 1 is 1. I'll add that here to get minus 6. I'll put a minus 6 there. Minus 6 times 1 is minus 6. Add those up, you get 0. That tells me the remainder is 0. And let's see. These numbers I got, are they the same as the coefficients in the result of division? So whenever you're dividing in x minus a constant, it's totally opaque as to why this is the right thing to do. I guess you can extract it and see like all of these numbers appear here somewhere. But so this, again, says the same thing. X minus 1 times 2x squared minus x, nope, plus x minus 6. So either way, we've now factored this polynomial. Let's talk about why you should care. How does this help us? So if I wanted to solve 2x cubed minus x squared minus 7x plus 6 equals 0, well, this thing is exactly equal to 2x squared plus x minus 6 multiplied by x minus 1. Does that second line look easier to set equal to 0? Yeah. It's two things multiplied together, then set equal to 0. The only way a product can be 0 is if one of the two things is 0. So that means that either x equals 1 or 2x squared plus x minus 6 equals 0. Does that purple thing I wrote down, is that something we know how to solve? Yeah, it's a degree 2 polynomial equation. Maybe you could try factoring it. Maybe it won't factor. But we can always use the quadratic formula. This will give me x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Feel pretty good? Maybe we'll check one thing first before we use a calculator, because I think I am definitely going to use a calculator. Double negative becomes positive. Ooh, let's put this in terms of this. The discriminant of this degree 2 polynomial, is it positive or negative? Do you remember when we talked about discriminants? The discriminant of a degree 2 polynomial is just the thing you see under the square root. Is the thing you see under that square root positive or negative? Positive, I think. Because right, it's 1 plus a positive. I don't know what it is without doing some arithmetic. So I know for a fact this will have this on its own will have 2 real solutions. And then there will be another one. So I think I'm going to see in total 3 real solutions. During the time I stalled, how many people just computed that? What'd you get? 1.5. 1.5? Yep. So 1.5 and negative 2. So the full family of solutions to this polynomial are x equals 1, 1.5, and negative 2. So here's the point of polynomial division. It lets you take a polynomial equation, reduce its degree by 1. That lets you find solutions more easily. And in fact, at this point, I think you can use this information to sketch a graph. I think it'll be degree 1 close to each of those terms, so it's a straight line next to each of them. You can use that to now sketch a graph. Neato. So, with 8 minutes left on the clock, hopefully people appreciated this quick review of polynomial division. So there will be some more for you to do. Let's do at least one more example. So here are 2 more polynomial equations. X cubed plus x squared plus x plus 1 equals 0. 2x cubed minus 10x squared minus x plus 5 equals 0. And I have provided you 2 solutions. So I think I'll give one of 2 options now. I'll pause. I can pause for a second. Let you talk through with those around you, one of the 2. And then we'll come together. Or I can talk through one more example of doing polynomial division. Should I go through an example, one of these? Okay. Then I'll do, so I think here's what I'll do. Those of you who want to do one on your own, do the top one. We'll go through this one together, those who would like to. So, factoring by grouping, polynomial on division, or synthetic division. Which one should we use? Factor by grouping, polynomial division, synthetic. Cool. Synthetic will be fewer steps. It has the downside that it unless you already know what it's supposed to mean, it's not informative. So you have to write like a concluding sentence. So let's do this. So I know that x minus 5 is going to be a root, so I need to realize this is x minus 5 times something. So to use synthetic division, you take this 5 and put it there. And now you just list the coefficients here. 2, negative 10, negative 1, 5. With me so far? And now I'll follow the same algorithm totally mindlessly on the previous page. So the first step is take this 2 and put it up there. Next, take 2, multiply it by 5. 2 times 5 is 10. Put that here with an addition sign. What's negative 10 plus 10? 0. So the next term is 0. Now just keep on going. 0 times 5 is 0, so I put a 0 here. Negative 1 plus 0 is negative 1. So I'll take a negative 1 and write it up there. All right. Negative 1 times 5 is negative 5. Remainder is 0. And when there is no remainder, maybe you don't need to write remainder is equal to 0, but sometimes it's nice to write. And especially when you know in advance it should divide in evenly, you know that remainder has to be 0. So let's write down what that tells us. That tells us 2x cubed minus 10x squared minus x plus 5 is equal to x minus 5, the factor that I knew in advance I would have, times 2x squared minus no x's minus 1. Did I make any errors in the process? And whenever you do this stuff, like, there were a lot of moving parts there. So you know what I'm going to do? I'm going to say, well, maybe I'm not totally confident, but I have access to the computer to check these things. So I think I'm just going to take a moment. I'm going to graph both the original original function I had and this factorization. If they're actually equal, I should see this in a graph. All right, 2x cubed minus 10x squared minus x plus 5, x minus 5 multiplied by 2x squared minus 1. Those seem to line up. All right, I think I believe the factorization. So back to the problem then. You take that and you set it equal to 0. Because, right, I wanted to set this equal to 0. Does that now look like something that we could just read off the solutions from? Yeah, okay, maybe that was a stretch. But does it now look like something we could split up into problems that are easier to solve? Yeah. So I know x equals 5 is the solution. That's the solution I already knew, so that's not surprising. Or 2x squared minus 1 equals 0. Does that look like an equation that's easy to solve? In fact, there's like no bx, so I think I can even just use, like I can just solve this directly. I don't need the quadratic formula. Add 1 to the other side, divide by 2, take the square root. Not saying that you couldn't use the quadratic formula, but the quadratic formula I think will be harder than necessary. So 2x squared equals 1, x squared equals 1/2, x equals plus or minus the square root of 1 over 2, which I'm going to simplify to square root 2 over 2. Neato. That feel okay? So we now have all 3 solutions. X equals 5, x equals square root 2 over 2, x equals negative square root 2 over 2. Make that negative sign readable. Ruby, that go all right? Nice. How many people would have included as their final answer just plus or minus 1 over the square root of 2? I guess that's all right at this stage. Once we get to trigonometry, I'll be a little bit more persnickety about wanting not to see square roots in the denominator. Good. So, with my remaining 40 seconds or so, this gives us a step. If you know a root to a polynomial equation, you can simplify it and hopefully then solve it. But that needs you to have this initial guess. You needed to know that x equals 5 was a solution. So the next trick we will get is the rational roots test, which will give us a list of candidates to be roots. No guarantee that it'll give us roots, but it'll give us a list of candidates to test. Sometimes it'll work, sometimes it won't. If it actually gives you roots, you can use those to reduce the degree of the polynomial. The law of signs is one last trick. Here's all it tells you. It tells you how many positive or negative roots to expect. If you can read it off, you can look at the coefficients, and then you can say something like, well, I know there must be either 5 or 3 or 1 root to a polynomial, positive root to this polynomial. But we'll get to that next time. I'm not behind right now. And I'm now actually done. Sorry, I went over my 45 seconds. Oh, I don't need to put my shoes back on. I stay here. Do you think a half hour is enough time to talk? Okay. Well, we can talk about something in the installment.
Okay.
If you want to show up a little bit early, I have a class that goes to like 10:50, but then I go right upstairs. So if you're a little bit early, we can have an extra 5 minutes. Yeah, hopefully we can get something out of this short chat. Otherwise, we'll figure out another time after. Yeah. Morning. Alright, see ya. It's like 7 minutes before start time. Excellent.
I was struggling on this one last week. I was going to talk to you on Friday, but then I listened to the lesson. I was like, oh, I can do something. And when I got to going into economics for an hour and I realized, oh, I better.
Okay. Yeah, let's talk through it. So let's start with just some setup. So
I did, I took out like the 5 out of it and I did
oh, it's not wrong. Yeah, that's a correct thing to do. So let's see. So let's write down both sides. So that was H1.
And also, when I graphed it, the height of it was 31.25, and I had no idea how that was gotten.
So, what did you graph to compare that 41 point whatever?
I just put it, I plugged it in the decimal.
Yeah, what did you plug in as those?
0 and 5 after doing quadratic formula. Oh wait, I think I did this. That's what I did. I just quadratic formula first and I went to that. I think.
So let's read the question, what the question is looking for. Because setting it equal to 0, that is how to do like when the ball lands. And I don't want to know where the ball lands. I want to know where.
So I also had to do that one.
Sure. So let's start with this. What does it mean for the two balls to collide?
They have to. The graphs have to line up.
The graphs have to line up.
Yes.
So that's like
analytical.
Yeah.
those two things.
Yeah.
There. So that's not a wrong way to do it. But here's the algebra way of doing it. These two graphs collide if their heights equal.
Yeah.
So let's do that. So this will be uniform that's minus 5, t minus 5. And what is height 2?
It should be like
Well, it's about
so if they go in and they're just like until like
and you need to open the last one.
and all of a sudden
Oh, okay. I mean,
Again, I had like, yeah, I had no idea.
so let's carry on from here. So our goal here is, so what's the degree of the polynomial?
I just didn't want to show up.
What's the biggest power on center? Not coefficient, power. So this is the degree of the polynomial. So if you want to point this out, it is so p squared minus 2c.
Yeah, okay, yeah.
Also degree 2. So this whole thing is a quadratic equation.
Yeah.
So you can like get everything onto the same side. Maybe you can apply the quadratic formula. So let's try to get everything onto the same side. And just simplify it. So yeah, cool. And maybe I'll move this out. Or maybe I will. Minus 5. Add that to the other side plus 5.
Oh my god.
And now, like, that stuff looks like complicated.
Did you go to school?
No,
Did you
no.
Was it just
No. So
Coverdale U?
I think here's the stretch. Take all that stuff, simplify it as much as you can,
What was it called?
and hopefully it becomes something that's easy to solve. You know it'll become something easy to solve. It's only degree 2.
So I do have the next one down. It's just that I have to transfer it to a PDF from my phone pictures.
Oh, okay.
So it's just
Yeah, I get it. There's like this extra technology stuff.
yeah. Thank you so much.
Yeah. I don't need it completely. There were some things that seemed intelligible.
I was just kind of lost. Because like there was a few parts that like I this shit I wanted to like or like was it not so I just wasn't sure how to do this.
Yeah. So let's do it by drawing kind of a generic picture. So what were the 2 points you know along the line?
-2
And in between sine. I know that point's on the graph. I don't know what that's between. But it could do literally anything. No idea what's happening. And you look to do the right thing. You shift it by 2 and by 1. And where do those 2 points go? Sounds right.
And that would be 2.
Right there is pretty easy. But
Yeah, because it's up 1. So you know those 2 points are on the graph, but otherwise you don't know. And now it's just this point. So -4 to 1, you just know it's on the line.
Like if 2, 7, 6,
smaller one is bigger. Would that be? Is it possible for that point to be on the graph? Or is the vertical line to say? Yeah, so the vertical line test says that if you have a single x value on the graph of the function, you can't have multiple y values.
Yeah, that's true. And the same thing for 2.5, I think. It's a vertical line test. And then 0, 3, and then 0, 1. So one of them.
Yeah, and in fact, either one could be possible. So both of these not have information.
Thank you.
Yeah.
I'll get that resubmitted.
All right, perfect. Thank you. Cool. Oh, okay, cool.
The text one that I have.
Okay. Yeah, so maybe I'll leave that question in general. I still have some. People need copies? Yeah. Cool. So, let's get started. So the last thing we did was an example of graphing a polynomial once it's factored. If you have a polynomial in a factored form, then you can graph. And let's just re-summarize what happened. So the example we did was, well, hopefully it's up there right now, right?